Afternoon everybody. Today we will discuss the next topic, that is SNI mechanism. In the last class we have studied the SN1 mechanism and SN2 mechanism. In the SN1 mechanism we obtain a retention of configuration, whereas in SN2 reaction we obtain the inverted product. So SNI mechanism, basically the name indicate that nucleophilic substitution reaction, but this mechanism is an internal nucleophilic substitution reaction in which we are usually using thionyl chloride as the reagent. And the speciality of the SNI mechanism is that the product in which the configuration is retained. See the example. This is a the tertiary alcohol, and the tertiary alcohol react with thionyl chloride, and thionyl chloride, so we will get the HCl is eliminated while the thionyl chloride react with the tertiary alcohol, and there is the bond between the carbon and oxygen is liberated and turned into the oxygen. So the oxygen become O minus, and the bond between the sulfur and chlorine is shifted towards the carbon atom. So the OH group is converted into alkyl halide. So this is the reaction. It is used for converting the alcohol to alkyl halide, and sulfur dioxide is eliminated as the byproduct. And this is a second order reaction. Both the substrate and thionyl chloride will influence the reaction. And as we discussed earlier, SNI, the name indicate that this is a nucleophilic substitution reaction in internal. And this SNI mechanism is very rare. There are only few examples or reactions are there in the nucleophilic substitution reaction in internal, and here the retention of the configuration will occur, and there is no possibility for the neighboring group participation in SNI mechanism. We know that in nucleophilic the neighboring group participation also, the configuration of the product is retained. And SNI mechanism follows second order kinetics. That means both the substrate and the concentration of the thionyl chloride is influence the rate of the reaction. And this is the reaction. Now we are moving into the another example. Here the secondary alcohol is treated with thionyl chloride. Usually the thionyl chloride is used for carrying out the SNI mechanism. But if we add the solvent, the reaction may change from SN1 to SNI to SN2. Okay, please remember, usually the thionyl chloride is used for making the substitution reaction as SNI, but in some case if we add some solvent like pyridine and some other solvent, acid, etc., the reaction may change from SNI to SN2. So in that case, in the SN2 case, we will get inverted product. See here, in this, first of all, secondary alcohol react with thionyl chloride, and as we discussed earlier, HCl is eliminated. Now the carbon oxygen bond is formed. Then after that, in first case we are adding HCl. So in presence of HCl, the HCl acting as a medium here, and in presence of HCl, SN2 reaction will occur. So that's why we will get an inverted alkyl halide. And in the second case, we are using OCH2CH2 twice, and here SN2 reaction is taking place. Even the transition state is involving the same transition state, but if we are adding the solvent, we will get SN2 reaction. But here if you are using OCH2, CH2, OCH2, CH2, in that case, first of all, SN2 reaction will occur. After that, again a second 2 reaction will occur. So, in that case, we will get a retention of the configuration. And in the middle case, we are used the solvent as an pyridine. So, in the pyridine, which is attacking the attacking the transition state in the opposite direction. So that's why we will get an inverted product, and this is an example for SN2 reaction. Whereas in the third case, that is an example for SNI, we will get a retention of configuration. So please keep in mind that we are usually using thionyl chloride for generating SNI mechanism, but the medium influences the reaction, and if you are using the pyridine as the medium, we will get an inverted product. This is mainly due to the reaction is undergone through SN2 reaction. So depending upon the solvent, the reaction may change from SNI to SN2. So SNI mechanism is very, very rare. Now we are moving into the next topic, that is neighboring group participation. Neighboring group participation also retain the configuration of the product. So we have studied SN1, SN2, SNI and neighboring group participation, and in the neighboring group participation 2 SN2 substitution take place. You know that in SN2 reaction, nucleophile attack in the opposite direction of the leaving group. So if the 2 SN2 reaction occurs, means there is a retention of the final product will occur. So let me moving into the mechanism of the neighboring group participation. In first step, attack of the internal nucleophile. So before that, we are just explaining the general character of the neighboring group participation. In always every neighboring group participation, there is a good leaving group and there is a electron donating group which contain either an pair of electron or a atom which have the capacity to donate the electron pair, and this atom is situated beta to the leaving group. Okay, now and this donating group will act as an internal nucleophile and form a 3-membered transition state. After that, the actual external nucleophile is entering the reaction medium, which is just opposite to the active involvement of the neighboring group, and the yield of the neighboring group is above 100%, and the configuration is retention of the configuration. These are the basic character of the neighboring group participation. Now we are moving into the mechanism. In the first step, the attack of the internal nucleophile, that is the group which having the lone pair of electron, I have shown by the letter G. So G is our internal nucleophile, and this internal nucleophile having the lone pair of electron, and the L is represented by the leaving group, which is a best leaving group. The capacity of the leaving group depending upon the stability of the negative anion or the size of the atom. If the size of the leaving group is high, it is a good nucleophile, and similarly if the negatively charged anion is stable, then also the leaving group is best leaving group. So here we use the best leaving group. So first of all, the leaving group, the bond between the carbon and leaving group may weaken. At the same time, the electron pair from the G is partially donated to the carbon atom. So we will get a 3-membered ring here. Okay, we will get a 3-membered ring here. Carbon, carbon and G plus. This is a 3-membered ring. And after that, the external nucleophile will approach the carbon atom. simultaneously the pair of electron which is donated by the G is picking the back donated to the or the retained by the G, and here in which we can see that in the first step leaving group is liberated. In the opposite direction the G will attack or donating the electron pair to the carbon atom. So that is the first SN2 reaction. And in the next case, second step, the nucleophile will approach to the carbon atom which is just opposite to the donation of the or retain of the electron pair to the G. So that is the second SN2. So the 2 SN2 will happen in the neighboring group participation. So that's why the configuration of the final product is retained. Okay. Now, which of the element are acting as a neighboring group? I already told you that any of the atom or bond which have the capacity to donate a pair of electron and which is situated to the beta position to the leaving group which act as a neighboring group. So there are lot of atoms act as a neighboring group: sulfur, oxygen, halogen group and pair of electron. So let us see the classical example. The classical example of the neighboring group participation is the reaction of the sulfur or the nitrogen or the halide with a nucleophile, and the rate of the reaction is much higher for the sulfur and nucleophile than it would be for primary alkyl chloride without heteroatom. See here in the example, the sulfur is situated to the beta position to the leaving group. Here the leaving group is bromine, and the beta position there is a sulfur atom is exist, and we know that in the sulfur atom there is a pair of electron is existing, and bromine is a good leaving group, so it will liberate its pair, it will liberate to the reaction medium by its pair of electron as Br minus. So that carbon is positive. So in order to reduce the deficiency of the electrons in that carbon, the electron pair is donated by the sulfur and to form a 3-membered ring, and in which the sulfur acquire a positive charge. Then the nucleophile, that is the external nucleophile, will appear in the opposite direction or in the same direction of the leaving group. So we will get the retention of the configuration. So here also the 2SN2 reaction occurs. That's why we will get a retention of the configuration. So here in this example, the sulfur act as a neighboring group participant. So if we take the same reaction instead of sulfur, we will not get the retention of configuration. We will get a inverted product because the reaction undergo the SN2 reaction. Now these are the another example. In the first example, the halogen act as a neighboring group. See here in this example, the iodine OH group is the act as a leaving group. We know that OH is not a best leaving group. For that we are adding HCl. So due to the presence of the H plus ion will pick out the pair of electron in the OH and to form an OH2 plus, and the pair of electron is donated to this OH2 plus and water is eliminated, and the iodine form a 3-membered ring, and this is an example for a neighboring group. Here the iodine in the lone pair of electron in the iodine act as a neighboring group. So keep in mind, remember that here we have two function group, iodine and OH. But we know that iodine is a best living group and OH is a poor living group. But iodine also contain a pair of electron. That's why here in this example, iodine act as a neighboring group. See the second example in which the NH2 act as a neighboring group, and as in the previous case, it forms a 5-membered ring. And in the last example, alkene act as a neighboring group. Here OTS act as a tosyl group act as a best leaving group, and the OTS is liberated, so the carbon become positive charge, and in order to remove the deficiency of the carbon atom, the pair of electron or the pi electron will coordinate to the positive charged carbon atom, and thus we will get a positive charge here. In the third resonance structure, it undergo the sigma bond will shifted towards this carbon atom, so the positive charge is shifted to other carbon atom. So in this example, alkene act as a neighboring group. See the fourth example in which oxygen act as a neighboring group. Consider in this example, this is a secondary alcohol, and in the beta position we have a chlorine, and we know that the chlorine is a best leaving group, but here the chlorine the hydrogen is donated in the presence of acid. OH group is coordinated, and here the oxygen act as a neighboring group and to form a 3-membered ring here, and the OH minus, that is the next nucleophile which is attacking in the opposite direction of the leaving group, so we'll get the retention of the configuration. I hope that you understood the concept. Thank you.